All right, we are streaming. Okay. Okay, so back to what I was doing earlier. You guys weren't here for this, but I mean, there's no one watching then and no one watching now anyway, so it's fine. Okay. All right. So, right. I need to write the. You know what? Real quick. Let me just go back into light. Light plus or light modern? I'll do light plus. Okay. All right, so we need to have our forward process. I haven't written a model in quite a bit, so we'll write this into a code. First, we need to. Okay, so we'll have base, have variable, create variable, which contains base image. I imagine it'd probably be, what would it be? Like, well, it wouldn't be NumPy, right? It would be a tensor of size, well, image size, I don't know, let's say it's 64 by, or no, it'd be 3 by 64 by 64, or 3 by x and y. 3 by x by y. That makes sense. We'll want to randomly sample from t randomly pick t from 0 to t terminal. That is not how I spell randomly, right? Yeah. Then apply noise to image based on t. I'll probably, okay, yeah, get noise from apply. I need to have another variable. Have other variable for image noised at t minus 1. Okay. What's the loss again for what is a loss for diffusion image models? Reddit. What is the loss for diffusion models? Yeah, we'll need VLB or elbow. VLB. Okay. Not quite sure what I where I should go from here. Just sad because I'm doing basically nothing so far. Let's see. I guess I should. I think I already have it. Yeah. All right. Background. Oh fuck it. Okay. So XT. What am I predicting again with? What am I trying to minimize in a basic D? I think it's DDPM, denoising, diffusion, probably. Yeah. Oh, bro. Okay, the expectation Tx0 epsilon theta. Let's want some music. Okay, forward process, backward process. XC minus 1 equals 1 over root alpha. Yo, we're probably gonna need to watch a video on diffusion models. It's really what's the output of this, or what variable is this supposed to be? Forward return x.view. This isn't trying to. Does this try and find the XT-1 image directly from the model? I thought the model was supposed to approximate the mean and the variance. Should I just read the paper? I mean, at this point, thinking about it. You spin me around, baby, right around. Okay, introduction. All right. Fuck me. You know what? We'll just read it. What the fuck is this guy talking about? Anyone gonna join me or what? Come on, guys. Does Discord not allow me to change, what's it called? To change my status anymore? Ah, there it is. Alright, let's read this. We present a high-quality image synthesis results using diffusion probabilistic models, a class of latent variable models inspired by consideration from our best results are obtained by training a weight variation and bound designed according to the novel connection between diffusion probabilistic models and denoising square matching with Langevin dynamics. I've heard of Langevin dynamics. I tried watching a video about them before, but it's very statistics heavy. I think, if I remember correctly, and I couldn't quite understand it. And our models naturally admit a progressive lossy decompression scheme that can be interpreted as generalization of autoregressive decoding. In the unconditional Sci410 dataset, we obtain an inception score of 9.64 and a state-of-the-art FID squared. What does FID stand for again? What does FID stand for? Fresh and inception distance. Okay. Alright. Oh, actually, let me start this. Okay. This paper presents progress in diffusion probabilistic models. Okay, this is not the first paper, you fucking whore. God damn it. Deep unsupervised learning using non-equilibrium thermodynamics. This should be good enough. Okay, is this specifically for creating images? No, it doesn't. Oh, maybe. Understand. Never gonna give you up. Never gonna let you down. Never desert you. Alright, well, let me read that. The variational inference to produce samples matched with data. Right time. Transition of the chain are learned to reverse a diffusion process, which is a Markov chain. Gradually adds noise to the data in the opposite direction of sampling until signal is destroyed. When the diffusion consists of small hold on. Your channel. Yeah. When the diffusion consists of small amounts of Gaussian noise, it is sufficient to set the sampling chain transitions to conditional Gaussians too. Okay. Diffusion models are straightforward to define with efficiency train, but to the best of our knowledge, there has been no demonstration that they are capable of generating high-quality images or show that diffusion models are actually capable of generating quality samples. Show that diffusion sometimes better than the published results in other types. Bro, this shit is fine. Okay. But their sample quality or models are not available for evidence. Background. Diffusion models 53, early variable models The form p theta of x0 is defined to be the integral of p theta x0 to t, dx1 to t. What does that mean? P theta, theta of x0, is p theta of x0 to t. So is that... I'm trying to think of this as a Riemann sum. What does that mean, an integral of p theta? If I'm correct, p theta is just a parameterized Gaussian, right? Alright. Where x1 to xt are latent to the same dimensionality as the data x0, sampled from q x0. A joint distribution p theta x0 to t is called the reverse process. You know what, let me ask ChatGPT. What specifically does this mean? The notation you've provided, hold on, is there a viewer? Let's see. If there's a viewer, say hi. No, I don't think so. Wow. Okay, well, who cares? Notation you've provided, yeah. Jesus, you have not copied this one. What even is this from? Oh, whoops. Say, this is from a diffusion paper. Actually, let me copy the entire phrase. Was it this one? No, this one. Why is there an integral? Are we summing over each dot? Okay. If I'm correct, p theta is a parameterized Gaussian distribution. If that's the case, why are we taking an integral? Shouldn't we be using a pi loop as its Markov chain? Oh, I think I see. I see, so... I think I see. I'm not sure I see anymore. So we have all these possible x0s, or paths towards x0s, and is that not a circular definition? Is this not a circular definition? The fuck is this song? Okay. Song is ass. Alright, this song is okay. Man, I love this camera though. Things that I'm lonely. Does Sora have a paper yet? Sora paper. No way. 27th of... Oh, actually? Oh, this is not official from OpenAI. Okay. I'm procrastinating reading this. Alright. Form of p theta of x0 is all probabilities of x0 or x1 to xt are latents of the same dimensionality as the data. x0 samples from q x0. Yeah. The joint distribution p theta x0 to t is called the reverse process. It is defined as a Markov chain with learned Gaussian transition starting at p xt equals the normal of xt No, I always get confused by this. What does xt over here mean? But it's a normal distribution, mean at 0, variance of I. Why is there xt within wouldn't n of 0 I? Couldn't be the same thing. Okay. P theta of x0 to t is defined as p of xt times the recurrent multiplication of p theta of xt minus 1 given xt. Okay. These are all probabilities, correct? Yeah. P theta of xt minus 1 given xt is defined as the normal of xt minus 1 calculated on xt minus 1 given mu theta, so the parameterized or approximated mean given xt and t, and the approximated variance given xt and t. What distinguishes diffusion models from other types of latent variable models is that the approximate posterior q of x1 to t given x0 called the forward process on diffusion forward process or diffusion process is fixed to a Markov chain that gradually adds Gaussian noise to the data according to a variance schedule b1 to bt. Okay. Q qx1 to t, that's d posterior, right? Qx1 to t given x0 is defined as the pi loop, I guess that could be called pi of qxt given xt minus 1 all the way up to t, and q of xt given xt minus 1 is defined as the normal of xt with a mean. I don't know why this is the variance schedule, but it seems that they found this to be good. The root of 1 minus bt of xt minus 1. How is bt calculated? I don't know. And bti for the variance. Training is performed by optimizing the usual variational lower bound on negative log likelihood, which is that the expectation of the negative log of p theta, we're taking the negative log likelihood of p theta given x0 is less than or equal to the EQ of negative log p theta x0. See, this is the part that is the most important and that I want to abstract away. A negative log likelihood. Goal in many probabilistic models is to maximize the likelihood of the goal in many probabilistic models is to maximize the likelihood of the observed data under the model, which is equivalent. Fucking hell, okay. The goal. So, say the probability of x0 is within some Gaussian distribution. What we're trying to do is have the second Gaussian distribution, which is the approximated x0, trying to maximize that overlap. So if I made a open paint, we have let's say this is true x0 rather than red. So true x0, something like this. And then we have some approximate x0, which is that. What we're trying to do is maximize that. That's how I understand it. But if we start with an actual x0, wouldn't we just have 100% over a single point? So the real, shouldn't it be a point like that, for example? Or let's say we know for a fact that this was the this was x0. Is that not, I guess it's still a distribution over one single point, and the rest being 0. We can still calculate the distance between these 100% distribution and that distribution. So you can still maximize. In that case, we're trying to tighten the distribution and have it completely overlap with this. If I understand correctly. Also, if when we get to some, xt, which is not 0, as we apply noise, then there should be variance. So the likelihood shouldn't be 100%. Yeah, let's define, actually, here real quick. 1 would be somewhere around here, let's say. This is 100%. As we apply noise, we'd be increasing the... Okay, so this is with noise applied. As we apply noise, let's say it starts as the probability is this, and then on the next time step it would be something like that. Okay, that's horribly done. And a couple time steps later we get to something like that. And so what we're trying to do is given some probability distribution, which is that, we want to find the posterior. Am I using that word correctly? Is posterior the distribution, the before distribution? There must be a better way of saying it. The before distribution. And what's the other one? It's posterior and oh fuck, I hate this song. Posterior. There's no way I have that up. Oh my god, bro. Posterior and prior, right? And prior the after. So if I said if we had some distribution x, t, and we were trying to approximate x, t minus 1, would that mean I'm trying to approximate the prior or the posterior? Or maybe this question doesn't even make sense. Okay. Guess it doesn't even really make sense. But also, what I should note is that it won't necessarily be centered over the last one. So it could end up, being a distribution like that. I think I understand. And we're trying to approximate that. Approximate these distributions. And what we're trying to maximize is the overlap between that distribution and ours. Or maybe not, it's some KL divergence shit, which I don't think is exactly an overlap. Do we measure the similarity of two distributions by the amount of overlap? Thanks. I fucking hate this new Reddit. Holy shit. Oh no. Gave away my Reddit name. No. Oh, who cares? Well, I kind of feel like browsing it, to be honest. Oh, the Jewish immigrants. Alright. But I guess he's not completely wrong. Smoked meat by Schwartz, right? That's right. I had some cheese curds today. I also had maple syrup today. Yeah, true. Yo, that's crazy. Hold on, let me read this. A 27-year-old technically living in the Bay Area and for Chandra. Okay, nerd. That's crazy, bro.
Why does finding
Bro. The graphic is just so bad, though. Operating loss. Honestly, I don't know.
Everyone in your life goes through menopause.
Actually, I'm kind of curious.
and I'm
Bro, shut up. Isn't Jon Stewart that fucking annoying guy? Yeah, that guy. Again, the biggest virtue signaler I've ever seen. Alright, we're procrastinating again. Come on, I need one viewer, bro. The summation involves the expected log ratio of the reverse process model p theta of xt minus 1 given xt to the forward process model q of xt given xt minus 1. What does this ratio tell us? And okay. As the model's prediction or approximation for the distribution at time t minus 1, given the state at time t, while q of xt given xt minus 1 is the actual distribution of xt given xt minus 1 defined by the diffusion process. This term aims to make the model's prediction for the reverse process denoising as accurate as possible relative to the true forward process. In essence, the objective L seeks to minimize the discrepancy between the model's distribution and the true distribution of the data across the entire diffusion process. This is achieved by optimizing the parameters theta of the reverse process model to make it as close as possible to the actual forward process. The distance being minimized is not a simple direct distance between two static distributions, but rather involves optimizing the model's parameters to accurately reverse the diffusion process. I don't really understand this. Huh. This does not make sense to me. Okay. Can anybody help me? Let's see. The fuck is trick on that? that actually how his name is spelt? I guess maybe in Germany it is. Bro, that's what I want to do. Here's what this one looks like. Bro. Okay, never mind. Started streaming 69 minutes ago. Why do we take the negative log likelihood? Why do we? I mean, I guess for gradient descent, but it's always ascend. Oh, whoops, not the likelihood. I meant rather than just the log likelihood. I guess maybe for gradient. Maybe so that we do gradient descent rather than ascent. But I don't see why that matters. Alright, I guess, I mean, it works right out of the box with, like, PyTorch and shit, so. This is not what I thought it was. Maybe, like, move it? Okay, what am I looking for again? Oh yeah. What does this ratio do? So that's less than or equal to. So let me just clarify this. I just want to clarify. This is the likelihood, negative log likelihood that p theta of x0. This is essentially the likelihood that our predicted x0 is within the true x0. Well, bro, I know. I'm just saying essentially. Oh, okay, so this is how probable we are to observe x0. Now, why do we take the expectation? Why do we take the expectation? Shouldn't minimizing be enough? All right. Okay. Alright, taking the expectation of the negative log likelihood instead of minimizing negative log likelihood directly for each observed data point x0 is crucial for several reasons, especially in the context of probabilistic models. The expectation averages the negative log likelihood across the entire data distribution. What does that really mean, though? This is essentially because we typically want to optimize the model parameters theta, not just for... Oh! Okay, I mean, this makes sense. 0, but across the whole distribution of data, minimizing expectation. So this just means we're taking an average overall. So this just means we're trying to minimize the average negative log likelihood rather overall over the entire batch rather than individual points. Okay, I mean, I feel like it could have been put more simply, but I don't know. Okay, why the fuck do we have this? What does this ratio represent again? What does the ratio represent again between P, theta, and Q? d theta xt minus 1. This term is the model's approximation of the reverse diffusion process. It represents the probability distribution of the state xt minus 1 given the subsequent state xt, as parameterized by theta. Essentially, is how the model predicts we can go back one step in the diffusion process, i.e. denoise or revert the denoising process by one time steps right from xt. Q of xt given xt minus 1. This term represents the forward diffusion process. Hold on. Well, no one's watching anyway, but still. Alright, well, I'll do it. Oh, why doesn't Discord show that I'm streaming? Discord doesn't show I'm streaming. Oh, okay. It's a OBS setting. Settings. What did it say to do? Discord streamer mode. What the fuck is that? Can I switch between these easily? Yeah, I can. Okay. Huh? I don't really get it. I don't really get how the ratio between the probability of xt and the probability of xt and the predicted probability x minus 1 tells me how correct my predicted probability is. is a conditional probability as opposed to a probability? I assume conditional probability is essentially the same, but essentially multiplied by some other probability and given to that probability, if that makes sense. Yeah, okay. Oh, I see. Alright, yeah. How the fuck did you come to the... When the model's reverse process P matches the forward process, it means the model has accurately learned the distribution of the original data through the reverse process. In a sense, has to undo the noise. How does this make it undo the noise? Think of it. I know this. I don't understand. What? Understand why this is true. With P theta, we get a probability distribution of xt minus 1. With Q, we get a probability distribution of xt. Why should xt minus 1, why should the probability of xt minus 1 the denoised data be equal to xt, the noised data? So is this basically saying that we should be able to recover the distribution that gave us xt? Okay, so if we end up with the probability, so if we can recover the probability distribution from xt minus 1, which gives us xt, how do we go from that to xt minus 1? Bro, is this not the... We're comparing two different... Why do we take the ratio of P, theta, and Q in diffusion model? I still do not understand why we compare these. Right here, why the fuck are we taking the ratio? This doesn't make sense to me. There you go. Oh, wait a minute. Maybe I'm starting to understand. Well, because essentially it's a Markov chain, right? So we have some event, and then so this is x0, and then it goes to x1, and it has like some probability, right? And we go to x2, that's some other probability. Let's say this is xt. The probability, well, okay, so all this has some probability, right? Let's say it's W%. If we move backwards from xt to x1 to x0, we'll end up with another probability distribution, right? So what they're saying is that if W, or in this case, we'll say if U, this is U%, saying if U is equal to W, then that's about equal. But I don't understand why that's true. Shouldn't we be aiming for this to become 100%? For U to get to 100%? Well, that's a probability distribution. I don't. I don't quite understand that yet. But why? But why do we want to match the theta? Variational lower bound. Okay, what matters is that we're trying to minimize the negative log likelihood of x0 given, using p theta. But alright, I finished. The fuck is a Bernoulli distribution? Okay, just a skewed Gaussian, that's what it looks like. Or dual modal, I mean. Doesn't matter. Oh, or it's a discrete distribution. What is a marginal? What is a marginal probability? Okay. If we multiply it by a weight, wouldn't that just scale it entirely? Oh yeah, no, that's what it does. Okay. Integral of p of x given z times pz? The fuck does that mean? Integrating over z. Bro. Given observation x, we can build a latent variable model. Yeah. with the variable z such that the distribution of interest p of x can be decomposed. P of x equals the integral of px given z of pz given. Alright. Condition our observations on some variables that we don't know. Therefore, the probability of observations will be the multiplication probabilities up.
Pulled you over? You sure you pulled me over? I am sure about that, because you were going 50 and my problem wasn't going.
How long have I been sharing for? About 2 hours, okay. You know what? I'll have this, even though it's the most important part, I'll just abstract it away. Although I'm curious, why does it say EQ rather than E? Why does it use EQ rather than E? Okay. For process variances, so it's less than or equal to this. So if you minimize that, then we should be good. P of xt. Negative log P. This isn't P theta, there's just P of xt. The forward process variances, BT can vary parameterization. Parallels constant as hyperparameters and expressiveness of the reverse process. They shouldn't part by the choice of Gaussian conditionals and P theta. With what's the same function form, BT are small. Null property of the forward process is that it admits sampling xt at an arbitrary time step t in closed form using the notation alpha t. It's defined as 1 minus beta t, and alpha t bar is defined as the product of alpha s. Oh, s equals 1 up to t. Alright. We have then q of xt given x0 is equal to the normal of xt using it's always confusing. Why put xt there? How is that any different? So, you know what? I'm just gonna go down a rabbit hole. Goes to the normal with a mean of root alpha bar t x0 times variance of 1 minus alpha bar t of I. Okay. Efficient tuning is therefore possible by optimizing random terms of L. What do you mean random terms? I suppose, actually. So further improvements come from variance reduction by rewriting L as... Bro, there's just so much. EQ is the KL divergence of QXT given 0, and P of XT. What is P of XT? What is P of XT? Would it not be uniform as is completely random? I did not type that right.
Gaussian. Imagine you take an image and add a bit of Gaussian noise to it. Then do this again. If we repeat this enough times, eventually we'll have an unrecognizable picture of static, a sample of pure noise. Now, what if we could figure out how to undo this process? That is, start from a noise image, gradually remove the noise, and end up with a coherent image. This is the basic idea behind diffusion models, an approach gaining traction in generative modeling. They've had success particularly in the domain of image generation, and they are starting to rival, and in some cases surpass, other kinds of generative models you may be familiar with on certain tasks. For example, recent diffusion models have outperformed generative adversarial networks, known as GANs, in perceptual quality metrics. And they've also shown impressive performance in various conditional settings, such as converting text descriptions to images, in-painting, and manipulation. In this video, we'll try to understand the basic mechanism behind diffusion models and how they can be adapted to different generative settings. We'll start with a sample from some target data distribution, like an image from a training set. Let's call this x0. Now, let's define a forward diffusion process that gradually adds noise to the image over big T time steps. Our model will be tasked with starting at x big T and undoing this noise through what we'll call a reverse process. The forward process, which we'll denote with Q, takes the form of a Markov chain, where the distribution at a particular time step only depends on the sample from the immediately previous step. So we can write out the distribution of corrupted samples conditioned on the initial data point x0 as the product of successive single-step conditionals. In the case of continuous data, each transition is parameterized as a diagonal Gaussian. Beta t here, each transition is parameterized. In the case of continuous data, each transition is parameterized as a diagonal Gaussian. Beta t here is the variance at a particular time step t. Typically, these variances are treated as hyperparameters and follow a fixed schedule for a particular training run. Beta generally increases with time and is restricted to be between 0 and 1, meaning that this coefficient, radical 1 minus beta t, will likewise be non-zero, but less than 1, bringing the mean of each new Gaussian closer to 0, coefficient radical, and is restricted to be between 0 and 1, meaning that this coefficient, radical 1 minus beta t, will likewise be non-zero, but less than 1, bringing the mean of each new Gaussian closer to 0. In the limit, as t approaches and likewise be non-zero, but less time, and is restricted to be between 0 and 1, meaning that this coefficient, radical 1 minus beta t, will likewise be non-zero, but less than 1, bringing the mean of each new Gaussian closer to 0. In the limit, as t approaches infinity, Q will approach a Gaussian centered at 0 with identity covariance, losing all information about the original sample. In practice, the total number of steps, big T, is on the order of 1,000. Using a large, albeit finite, number of steps allows us to set the individual variances, beta t, to be very small, while still approximately maintaining the same limiting distribution. But why do we want to use a small step size? What's the benefit? Well, it means that learning to undo the steps of the forward process won't be too difficult. Let's consider a simple case in one dimension. Suppose we were given the distribution of a forward process sample at time t-1, and it resembled a mixture of Gaussians with two modes. We then observe xt, and want to infer the posterior distribution over xt-1. That is, we'd like to determine where did the chain likely come from in order to arrive at xt. What was the previous step of the chain? If the noise step, that is q of xt given xt minus 1, is allowed to be large, then we will be quite uncertain so the forward process won't be too difficult. Let's consider a simple case in one dimension. Suppose we were given the distribution of a forward process sample at time t minus 1, and it resembled a mixture of Gaussians with two modes. We then observe one. Suppose we were given the distribution of a forward process sample at time t minus 1, and it resembled a mixture of
So that's the probability of xt, if I understand correctly.
Gaussians with two modes. We then observe xt, and want to infer the posterior distribution over xt minus 1. That is, we infer the posterior distribution over xt minus 1. Resembled a mixture of Gaussians with two modes. We then observe xt, and want to infer the posterior distribution over xt minus 1.
Are you saying you want to see what's already there, or distribution on screen, or the distribution of xt minus 1?
That is, we'd like to determine where did the chain likely come from in order to arrive at xt. What was the previous step of the chain? If the noise step, that is q of xt given xt minus 1, is allowed to be large, then we will be quite uncertain about the location of xt minus 1. Who knows where we jumped from? But if the forward noise step is restricted to be small, there is much less ambiguity
Bro.
about xt minus 1. If that is, we'd like to determine where did the chain likely come from in order to arrive at a mixture of Gaussians with two modes. We then observe xt, and want to infer the posterior distribution over xt minus 1. That is, we'd like to determine where did the chain likely come from in order to arrive at xt. What was the previous step of the chain? If the noise step, that is q of xt given xt minus 1, is allowed to be large, then we will be quite uncertain about the location.
What's the difference between q of xt given xt minus 1 and q of xt minus 1? What's the difference between q of xt given xt minus 1 and q of xt minus 1? Okay, I think I understand. So this over here is telling us, bro, this is telling us the probability that we observe xt given some xt minus 1. But why is this a distribution? Is this distribution saying that if xt minus 1 is here, then our probability of observing xt is this? I think this is saying that given some xt minus 1, the probability of all xt's is that.
If the noise step, that is, determine where did the chain likely come from in order to arrive at xt, what was the previous step of the chain? If the noise step, that is, q of xt given xt minus 1, is allowed to be large, then
this is saying there's some probability that xt minus 1 was any of these.
then we will be quite uncertain about the location of xt minus 1.
But wouldn't that be given xt? Yo! Saying the probability of xt minus 1, of our current xt minus 1, is this given xt. Probability of xt given xt minus 1. So if xt minus 1 is over here, we have a low likelihood of observing xt. And this is the likelihood of observing any xt given an xt minus 1.
Who knows where we jump from? But if the forward noise step is restricted to be small, there is much less ambiguity about xt minus 1.
So this is essentially saying that xt minus 1 could be in these bounds over here. There's a likely to have been in these bounds because there's like a 3% chance that this xt minus 1 could have given us this. Like a really high percent chance that xt minus 1 would have given us that. That if we have xt minus 1, we'll have this. Okay. This is saying that q of xt minus 1 given xt. Bro.
Location of xt minus 1. Who knows where we jump from? But if the forward noise step is restricted to be small, there is much less.
I think I see. So this is xt or xt minus 1. Let's say it's xt minus 1. That's telling us the probability of xt minus 1. Right, given that we have some xt. Now the probability that this xt was generated by this xt minus 1 is high, right? And it would drop off. So this would be the peak of that. I think I'm starting to understand.
Less ambiguity about xt minus 1. We could then be justified in modeling the posterior of the forward step, that is, q of xt minus 1 given xt, with a unimodal Gaussian, eliminating the contribution from the mode to the right. And in fact, it can be shown theoretically that in the limit of infinitesimal step sizes, the true reverse process will have the same functional form as the forward process. So diffusion models leverage this observation, parameterizing each learned reverse step to also process, shown theoretically that in the limit of infinitesimal step sizes, the true reverse process will have the same functional form as the forward process t, with a unimodal Gaussian, eliminating the contribution from the mode to the right. And in fact, it can be shown theoretically that in the limit of infinitesimal step sizes, the true reverse process will have the same functional form as the forward process. So diffusion models leverage this observation, parameterizing each learned true reverse process will have the same functional form as the forward process, with a unimodal Gaussian, eliminating the contribution from the mode to the right. And in fact, it can be shown theoretically that in the limit of infinitesimal step sizes, the true reverse process will have the same functional form as the forward process. So diffusion models leverage this observation, parameterizing each learned reverse step to also be a unimodal diagonal Gaussian. Aside from the sample at time t, the model...
Bro. I think I might just be fucking retarded. Like, bro.
Models leverage the same functional form as the forward process. So diffusion models leverage this observation, parameterizing each learned reverse step to also be a unimodal diagonal Gaussian.
Okay. Alright, that makes sense. Yeah, because we proved that earlier.
Aside from the sample at time t, the model also takes t as input in order to account for the forward process variance schedule. Different time steps are associated with different noise levels, and the model can learn to undo these individually. Like the forward process, the reverse process is set up as a Markov chain, and we can write out the joint probability of a sequence of samples as a prop chain. Like the forward process, the reverse process is set up as a Markov chain, and we can write out the joint probability of a sequence of samples as a product of conditionals and the marginal probability of x big T. So what is P of x big T here exactly? Well, it's the same as Q of x big T, the pure noise distribution. So at inference time, in order to actually generate a sample, we start from the Gaussian and begin sampling from the learned individual steps of the reverse process, P of xt minus 1 given xt, until producing an x0. Okay, great. So we've defined these forward and reverse diffusion processes. The forward process is designed to essentially push a sample off the data manifold, turning it into noise. And the reverse process is trained to produce a trajectory back to the data manifold, resulting in a reasonable sample. But what objective will we actually be optimizing? Is it some maximum likelihood objective where we directly maximize the density assigned to x0 by the model? Well, not exactly. If we try to calculate P of x0, we see that we have to marginalize over all the possible trajectories. Say P of x0 model? Well, not exactly. If we try to calculate P of x0, we see that we have to marginalize over all the possible trajectories, all the ways we could have arrived at x0 when starting from a noise sample. This, unfortunately, is intractable. But it turns out we can maximize a lower bound. To do this, let's view x1 over all the... If we try to calculate P of x0, we see that we have to marginalize over all the possible trajectories, all the ways we could have arrived at x0 when starting from a noise sample. This, unfortunately, is intractable. But it turns out we can maximize a lower bound. To do this, let's view x1 through x big T as latent variables and x0 as an observed variable, allowing us to interpret a diffusion model as a kind of latent variable generative model. If we think...
Why is this zooming? I don't want you to zoom, bro. Alright, you good now? I'll keep you like this.
Think back to another latent variable model you may be familiar with, variational autoencoders, commonly known as VAEs. We might get a hint about our training objective, coders. We think of the diffusion model as a kind of latent variable generative model. If we think back to another latent variable model you may be familiar with, variational autoencoders, commonly known as VAEs, we might get a hint.
Zoom in again? There's no shot. Why are you zooming in? Bro, I ain't gonna lie, I didn't even know this existed. Zoom factor. fuck is zoom factor? Don't be zooming on me, bro. All right.
About our training objective. As a quick reminder, as a kind of latent variable generative model. If we think back to another latent variable model you may be familiar with, variational autoencoders, commonly known as VAEs, we might get a hint about our training objective. As a quick reminder, in a VAE, we have an encoder that produces a distribution over latency given a data input x, and a decoder that reconstructs the data by producing a distribution over data x given the latent input z. So we can think of the forward process in diffusion models as analogous to the encoder, producing latents from data, and the reverse process as analogous to the decoder, producing data from latents. Now, unlike a VAE encoder, the forward process here is typically fixed. It's the reverse process that we focus solely on learning. This means that only a single network needs to be trained, unlike in a VAE where two networks are trained jointly. So we can now borrow the basic training objective used by VAEs and a number of other latent variable models. When we have a model with and the reverse process as analogous to the decoder, producing data from latents. Now, unlike a VAE encoder, the forward process here is typically fixed. It's the reverse process that we focus solely on learning. This means that only a single network needs to be trained, unlike in a VAE where two networks are trained jointly. So we can now borrow the basic training objective used by VAEs and a number of other latent variable models. When we have a model with observations x and latent variable z, we can derive what's called the variational lower bound, also known as the evidence lower bound, a lower bound on the marginal log likelihood p theta of x. We won't walk through the full derivation here, but the end result is a likelihood term, also known as a reconstruction term, subtracted by a KL divergence term. The likelihood term encourages the model to maximize the p and latent variable z, so we can now borrow the basic training objective used by VAEs and a number of other latent variable models. When we have a model with observations x and latent variable z, we can derive what's called the variational lower bound, also known as the evidence lower bound, a lower bound on the marginal log likelihood p theta of x. We won't walk through the full derivation here, but the end result is a likelihood term, also known as a reconstruction term.
That's funny. That's funny. Oh, never mind. You guys can't see what I'm looking at. I'm looking at some funny Twitter. Bro, how is she still going? What the fuck? She drank that whole thing, yo. That's crazy. That's crazy. Ugh, we all suck. Oh, I can't, bro. I really hope someone doesn't go back and watch this stream.
Watch out! Watch out!
The fuck am I reading? Okay. Dingboard is actually being used. How to see how many hits a site gets? Yeah, you know what? I'll use Google Analytics or Google Trends, I guess. I'm just curious if this is ever used or ever looked up. Dingboard as a topic. Yeah. Dingboard, worldwide. Okay, there's some searches for it, but it past 30 days per month. Oof. Okay, 2004 to present. It doesn't look like there's that much. Sometime in 2010 there was some. Anyways, pretty sure it makes like almost 10,000 a month, right? Maybe, I don't know. What? What does pro-nuclear have to do with any of these? And why are oil and coal companies with climate change activists? What does this meme mean? Okay.
Subtracted by a KL dimension as the evidence lower bound. A lower bound on the marginal log likelihood, P theta x. We won't walk through the full derivation here, but the end result is a likelihood term, also known as a reconstruction term, subtracted by a KL divergence term. The likelihood term encourages the model to maximize the expected KL, also known as variable z models. When we have a model with observations x and latent variable z, we can derive what's called the variational lower bound, also known as the evidence lower bound. A lower bound on the marginal log likelihood, P theta x. We won't walk through the full derivation here, but the end result is a likelihood term, also known as a reconstruction term, subtracted by a KL divergence term. The likelihood term encourages the model to maximize the expected density assigned to the data, while the KL divergence encourages the approximate posterior QZ given x to be similar to the prior unlatent variable P of z. As we saw earlier, x0 will serve as the observation in the diffusion model framework, while x1 through big T will take the place of the latent variable z here. Let's substitute these in. Alright, now let's simplify it a bit. We can expand the KL divergence to combine the two terms into a single expectation. And finally, we can refactor the chain probabilities into their individual steps. Now, there's a nice property of the forward process Q that we didn't touch on earlier. Any arbitrary step of the forward process can be sampled directly in closed form. This is just because the sum of independent Gaussian steps is still a Gaussian. So at training time, any term of this objective can be obtained without having to simulate an entire chain. Likewise, we can optimize this objective by randomly sampling pairs of xt minus 1 and xt, and maximizing the conditional density assigned by the reverse step to xt minus 1. However, because different trajectories may visit different samples at time t minus 1 on the way to hitting xt, this setup can have high variance, limiting training efficiency. To help with this, we can rearrange the objective as follows. Let's examine each component. P of x big T is fixed. It's just the start of the reverse process, the pure noise distribution. And as we saw earlier, the whole forward process Q is also treated as fixed. So we just have to worry about these two terms to the right. Here we have a sum of KL divergences, each between a reverse step and a forward process posterior conditioned on x0. One can prove with Bayes' rule that when we treat the original sample x0 as known, like it is during training, we have to worry about these two terms to the right. Here we have a sum of KL divergences, each between a reverse step and a forward process posterior conditioned on x0. One can prove with Bayes' rule that when we treat the original sample x0 as known, like it is during training, these Q terms are actually just Gaussians. Since the reverse step is already parameterized as a Gaussian, each KL divergence now is simply comparing two Gaussians and can be evaluated in closed form. This helps reduce variance in the training process because instead of aiming to reconstruct Monte Carlo samples, the targets for the reverse step become the true posteriors of the forward process, given x0. There are a couple different ways we could imagine implementing the reverse step, P theta. In the paper, the Noisy Diffusion Probabilistic Models, DDPM for short, the authors elect to set the reverse process variances to time-specific constants, as they found learning them led to unstable training and lower quality samples. So the reverse step network is solely tasked with learning means. They then suggest a reparameterization that aims to have the network predict the noise that was added rather than the Gaussian mean. First, we can rewrite sampling from an arbitrary forward step by using an auxiliary noise variable, epsilon. Epsilon here has a constant distribution, independent of the forward time step t. And the reverse step model can be designed to simply predict this epsilon. The authors also found that a simpler version simply independent of the forward time step model would predict the noise that was added rather than the Gaussian mean. First, we can rewrite sampling from an arbitrary forward step by using an auxiliary noise variable, epsilon. Epsilon here has a constant distribution. independent of the forward time step t, and the reverse step model can be designed to simply predict this epsilon.
Oh, I see. I think. So we're taking the squared error. WT. What's WT? What the fuck is WT? Where was W defined? Okay. Alright. But this looks to be the mean error of epsilon minus theta epsilon. So we're trying to predict what noise was predicted or was added.
The authors also found that a simpler version of the variational bound that discards the term weights that appear in the original bound led to better sample quality. So compared to the original variational lower bound, their objective downweight steps that have very small noise at early time steps of the forward process, allowing training to focus on more challenging, greater noise steps. Like other generative frameworks, diffusion models can be made to sample conditionally given some variable of interest, like a class label or sentence description. One way to do this is to just feed the conditioning variable y as an additional input during training. In theory, the model should learn to use y as a helpful hint about what it should be reconstructing. In practice, some work has shown that further guiding the diffusion process with a separate classifier can help. In this setup, we take a trained classifier and push the reverse diffusion process in the direction of the gradient of the target label probability with y as an additional input during training. In theory, the model should learn to use y as a helpful hint about what it should be reconstructing. In practice, some work has shown that further guiding the diffusion process with a separate classifier can help. In this setup, we take a trained classifier and push the reverse diffusion process in the direction of the gradient of the target label probability with respect to the current noise image. And we can do this not just with single word labels, but also with higher dimensional text descriptions as well. Of course, one drawback of this technique is the reliance upon it.
Bro, I want to pay someone to like guide me through this. Okay, this fucking shit is annoying me. I think I might swear too much. The fuck am I doing? Oh.
Second network. An alternative approach eliminates this reliance, instead using special training of the diffusion model itself to guide the sampling. In the paper Classifier-Free Diffusion Guidance, the conditioning label Y is set to a null label with some probability during training. Then, at inference time, the reconstructed samples are artificially pushed further towards the Y conditional direction and away from the null label. Even though no new information is being given to the model, they found this to produce higher quality samples under human evaluation compared to classifier guidance. In-painting is another conditional generation problem where diffusion models have had success. The naive way to perform in-painting with diffusion models is to take a model trained in the standard way, and at inference time, replace known regions of an image with a sample from the forward process after each reverse step. Now, this works okay.
Did you hear? Permanent residency in Canada has become the most worry-free it's ever.
Welcome to this tutorial on how to implement a denoising diffusion model in PyTorch. On YouTube, I've already watched several great tutorials on these models.
I think I'm gonna be right back. We'll be right back. Alright, we are back. I have an expander in now, so I can't, talk. Jesus Christ. I can't talk completely normally. Really quick, I just want to look at something.
However, so far there's very few hands-on content. Because of that, I created another Colab notebook with an implementation of a simple diffusion model, and throughout this video I explain both the theory and the implementation and hope that you find it useful. With diffusion models, we are in the domain of generative deep learning. That means we want to learn a distribution over the data in order to generate new data. There are already lots of model architectures available to generate new data, for example, generative adversarial networks and variational autoencoders. I found this figure in NVIDIA's blog, which summarizes it quite nicely. VAEs and also normalizing flows have shown to produce diverse samples quickly, but usually the quality is not great compared to GANs. As a recap, a VAE compresses an input into a latent distribution and then samples from this distribution to recover the inputs. After training, we can sample from the latent space to generate new data points. Usually VAEs are quite easy to train, but as mentioned, the outputs can be blurry. GANs, on the other hand, produce high-quality outputs, but are most of the time difficult to train. This stems from the adversarial setup, which can cause problems such as vanishing gradients or mode collapse. I have to say that I experienced lots of these issues myself throughout the years. Of course, there are already lots of improvements nowadays, but still it's not that easy to fit such a model. As you probably know, the diffusion model is a rather new generative deep learning model that has shown to produce high-quality samples which are also quite diverse. Diffusion models are part of a lot of modern deep learning architectures and recently showed great success in text-guided image generation, such as in DALL-E 2 or ImageGen. I'm pretty sure you have seen this in the media. Diffusion models work by destroying the input until noise is left over and then recovering the input from noise using a neural network. More details will follow later in this video. Of course, diffusion models also have their downsides, for example the sampling speed. Because of the sequential reverse process, they are much slower compared to GANs or VAEs. But as these models are still in their infancy, there might be lots of improvements in the future. Using that as motivation, let's try to build a simple diffusion model by ourselves. More specifically, we will fit a diffusion model on an image dataset. The architecture and model design are mainly based on the following two papers. The paper on the left from researchers from Berkeley University was one of the first publications that uses diffusion models for image generation. The researchers demonstrate what this model is capable of and also introduce some nice mathematical properties. The paper on the right from OpenAI can be seen as a follow-up with several improvements that make the image quality even better. For example, they use additional normalization layers, residual connections, and more. In my simple example, I don't plan to build the latest state-of-the-art architecture, but instead just want to build a solid base model. Finally, I want to point out that this video is focused on the implementation and not all of the theoretical details. Of course, I will explain everything that is required to follow along, but in case you really want to get a deeper understanding, you might want to have a look at one of the great resources collected on this GitHub page. With that being said, let's continue with answering some immediate questions about implementing diffusion models in a fast-forward mode. First question, what are actually diffusion models? Diffusion models work by destroying some input, for example an image, by gradually adding noise, and then recovering the input from the noise in a backward process, also called denoising. This is also called a Markov chain because it's a sequence of stochastic events where each time step depends on the previous time step. A special property of diffusion models is that the latent states have the same dimensionality as the input. The task of the model can be described as predicting the noise that was added in each of the images. That's why the backward process is called parametrized. We use a neural network for it. In order to generate new data, one can simply perform the backward process from random noise and new data points are constructed. A typical number of steps that is chosen in this sequential process is 1000. However, of course, the larger this number is, the slower the sampling will be. Next question, how do you start implementing such a model? We will need mainly three things for that: a scheduler that sequentially adds noise, a model that predicts the noise in an image, which will be a UNet in our case, and finally a way to encode the current time step. We will dig deeper into each of these components, but first let's have a look at our dataset. So this is the Colab notebook, and the dataset we use is called Stanford Cars, which is included in PyTorch, and it consists in total of around 16,000 images, 8,000 train and 8,000 test images. Of course, as we build a generative model, we can use all of them. So we have 16,000 images, and here are some samples of them. Later I will crop them to the same size and reduce the size a bit to make the learning faster. As you can see, the cars in these images are in many different poses with a variety of backgrounds, so we should expect a lot of diversity in our generated images, which we will also see later. Of course, there's no need to reinvent the wheel. There are already some existing implementations of diffusion models, and this notebook is highly inspired by these implementations, which means I got a lot of the code from these two resources. Implementing the diffusion model consists of several steps, mainly the forward process, the backward process, the loss function, and then we can already define sampling and training. And before we start looking at the forward process, let's talk about it in more detail. Even though I try to keep it practical, we have to talk about some of the math of diffusion models. The forward process is fairly easy. All we need to do is to add noise to the images. This Markov process is usually denoted with Q, and the noise that is added to an image depends only on the previous image. X0 is always the initial input, and all other X's are more and more noisy versions of it. The way how noise is sampled is described by this formula. It's a conditional Gaussian distribution with a mean that depends on the previous image and a specific variance. Let's inspect this term more closely. The sequence of betas is a so-called variance schedule that describes how much noise we want to add in each of the time steps. xt-1 is the previous sequence of betas. We try to keep it practical, we have to talk about some of the math of diffusion models. The forward process is fairly easy. All we need to do is to add noise to the images. This Markov process is usually denoted with Q, and the noise that is added to an image depends only on the previous image. X0 is always the initial input, and all other X's are more and more noisy versions of it. The way how noise is sampled is described by this formula. It's a conditional Gaussian distribution with a mean that depends on the previous image and a specific variance. Let's inspect this term more closely. The sequence of betas is a so-called variance schedule that describes how much noise we want to add in each of the time steps. xt-1 is the previous, less noisy image, which means the mean of our distribution is exactly the previous image multiplied with this term that depends on the variance schedule beta. The variance of this normal distribution is fixed to beta multiplied with the identity. I thought it makes sense to gain some more intuition about beta.
Lucidchart makes intelligent diagramming easy and helps your best ideas become real.
As you probably know, each of the pixels in an image has 3 channels, red, green, and blue. These values are usually between 0 and 255, or when normalized between, for example, -1 and 1. Let's take this giant red pixel with a color code of 1, -1, -1. So we have a lot of red, but no green and no blue. According to the previous formula, the distribution of our next image is now described by this mean and variance. That means the values of our red pixel multiplied with the square root of 1 minus beta is exactly the mean of our distribution for that single pixel. Depending on the noise level beta, this could for example be 0.99 for the first image. The variance is fixed to beta. If we choose a large beta, it means that the pixel distribution is not only wider but also more shifted, which results in a more corrupted image. But choose a large beta, it means that the pixel distribution is not only wider but also the first image. The variance is fixed to beta. If we choose a large beta, it means that the pixel distribution is not only wider but also more shifted, which results in a more corrupted image. When sampling from this distribution, we consequently end up with more noise. Eventually, beta controls how fast we converge towards a mean of 0, which corresponds to a standard Gaussian distribution. I recommend to try out different values to see how the means converge towards 0. The important part is to add the right amount of noise, such that we arrive at an isotropic Gaussian distribution with a mean of 0 and a fixed variance in all directions. Otherwise, the sampling later will not work. That means we don't want to add too few noise, but also not too much in order to have a too noisy image too early. There are different scheduling strategies for that. In our case, we will simply add the noise linearly, but in the literature there are also choices like quadratic, cosine, sigmoidal, and more. I said that the noise is added sequentially in this formula, but actually the researchers proposed an even better solution. Because the sum of Gaussians is still a Gaussian distribution, we can also directly calculate the noisy version of an image for a specific time step t. And that's without sequentially iterating over its predecessors. Based on the initial image x0, we can sample the noisy version of it for any arbitrary time step t. For this, we need to pre-calculate the closed form of the mean and variance based on the cumulative variance schedules. Let's see an example of this to better understand it. Let's say we choose 200 steps in our diffusion process. The variance schedule beta tells us how much noise we want to add in each of the steps. We linearly increase it until a maximum value of 0.02. If we wouldn't increase it at all, it would take forever to end up with pure noise. The authors now define the term alpha, which is simply 1. We linearly increase it until a maximum value of 0.02. If we wouldn't increase it at all, it would take forever to end up with pure noise. The authors now define the term alpha, which is simply 1 minus beta. I like to think of it as a number that tells us how much information of the original image we keep when transitioning from one image to the next. By calculating the cumulative as to end up with pure noise. The authors now define the term alpha, which is simply 1 minus beta. I like to think of it as a number that tells us how much information of the original image we keep when transitioning from one image to another. The authors now define the term alpha, which is simply 1 minus beta. I like to think of it as a number that tells us how much information of the original image we keep when transitioning from one image to the next. By calculating the cumulative product of these alpha terms, we get a new term denoted as alpha over line. With this, we can specify a new distribution that allows us to sample for a specific time step. Now that's the high-level explanation. For more details, I recommend to have a look at the extraordinary explanation video by Outlier that captures all the mathematical derivations for which I didn't have time here. A consequence for our training will be that we simply sample a time step t and pass the noisified version of it to the model. That makes the training much easier and smoother compared to sequentially iterating over the same image. That was mostly it regarding the forward process. Let's jump into the code and see how we can implement it. Alright, let's have a look at the noise scheduler. This is mainly inspired from the GitHub implementation. First, we have a function that defines a linear beta schedule. We use torch linspace for that, which interpolates between two values for as many time steps as we define. So these are the betas. And then this is just a helper function that extracts a specific index from a list and also considers the batch size, so we can use it later and during training. And the main function is forward diffusion sample during training. And And the main function is forward diffusion sample, which will use some pre-calculated values from here. And those are exactly the values
What the fuck is cumprod?
I just mentioned, so we calculate the alpha diffusion later and during training, and considers the batch size. So we can use beta schedules for as many time steps as we define. So these are the betas. And then this is just a helper function that extracts a specific index from a list and also considers the batch size. So we can use it later and during training. And The main function is forward diffusion sample, which will use some pre-calculated values from here, and those are exactly the
Oh, cumulative products. Oh my god.
the values I just mentioned. Main function is forward diffusion sample, which will use some pre-calculated values from here. And those are exactly the values I just mentioned. So we calculate the alphas and then the alpha with the overline. So we calculate the alpha and then the alpha with the overline and some additional terms so that we can calculate the noisy version of an image. So this function takes as input x0, the initial image, and the time step t, and it returns the noisy version at time step t of that specific image. And so what's happening in this forward diffusion sample function is that it returns the noisy version at time step t of that specific image. And some additional terms so that we can calculate the noisy version of an image. So this function takes as input x0, the initial image, and the time step t, and it returns the noisy version at time step t of that specific image. And so what's happening in this forward diffusion sample function is that we sample some noise and then get the time step specific values that are pre-calculated. So we get and then get the forward diffusion sample function is that and so what's happening in this forward diffusion sample function is that we sample some noise. And then get the time step specific values that returns the noisy version at time step t of that specific image. And so what's happening in this forward diffusion sample function is that we sample some noise and then get the time step specific values that are pre-calculated. So we get a specific index from all of these pre-calculated lists. For alpha overline, square root, and all of that. And then we simply calculate the new sample based on the original inputs plus the noise, and this gives us the noisy. Version of an image at a specific time step. So next we can try that out on our data set, but in order to do that we first have to put our data set into a PyTorch data. Loader. And also our images at the moment are pillow images, which means we first have to convert them into tenders. And as mentioned before, I resized the
Hmm?
Images. To that into a PyTorch data loader. And also our images at the moment are pillow images, which means we first have to convert them into tensors. And as mentioned before, I resized the images to a shape of 64 by 64, which is relatively small, but makes the training much faster. And then I do some data augmentation things like horizontal flips. And then I call toTensor, and this scales the data between 0 and 1. And now I mentioned that we need to have the data in a range of -1 to 1 in order to work with these betas. And because of that, this last transformation converts our data into our desired range. And that
I'm changing chairs very quick. Shit, my belly button's showing, bro.
That is because...
You know what? Hold it. This is not too comfortable. Let me get my pillow. Let's see. Will this work? I hope so. Kinda. It's alright.
Because if we multiply that by 2, we have a scale of 0 to 2. And then if we subtract 1, we end up in the desired range of -1 to 1. And then, as mentioned before, I load both the train and test set, and then I merge them into a so-called concat dataset, which holds all of the images. And then I have a second function that does exactly the reverse direction. It converts a tensor image into a pillow image and applies all of the reverse transformations that we did here. And after that, it simply shows or prints the image. And if we have a batch of images, we just take the first image to display it in our...
This one. Variational lower bound. Okay, what matters is that we're trying to minimize the negative log likelihood of x0 given, using p theta. what matters is that we're trying to minimize the negative log likelihood.
Interpret a diffusion model as a kind of lately very energy model. If we think
Why is this zooming? I don't want you to zoom, bro. I don't want you to zoom, bro.
and is restricted to be
in a fast forward mode. First, main function is forward diffusion sample during training. And
Whoops. Oh shit, my belly button's showing, bro. You know what? Hold up. This is not comfortable. Let me get my pillow. Let's see. Will this work? I hope so. Alright, I'm back.
Or notebook. And with that, we load the data set. So train and test splits, and then put everything into a data loader in our notebook. And with that, we load the data set, so train and test splits, and then put everything into a data loader. And here we can simply iterate over one batch and see how we convert an image in.
Where the fuck do I use SciPy, bro? I don't have it installed. Whoops. Okay.
into more and more noise so that we end up with pure noise. So now after finishing the 4 bit, we end up with pure noise. So one batch and
Holy shit, how much data does it take? $2.6 gigs. Fuck. How much data do I have? I don't know. I'm going to do security data.
and see how we
Bro, I don't get it. Oh, yeah, I'll just ask GPT. Uh, what?
We convert an image into more and more noise so that we end up with pure noise.
No way it works. What was different? What was I... Oh, holy bro. That's why. Bruh.
So now after finishing the forward process, let's have a look at the neural network model in the backward process. The authors propose to use a UNet. This is a special neural network that has a structure that is similar to the one used in an autoencoder. UNets are a popular model for image segmentation, and their output has the same shape as the input. The input passes a series of convolutional and downsampling layers until a bottleneck is reached, and then the tensors are upsampled again and pass more convolutional layers. The input tensors get smaller but also deeper as more channels are added. Besides that, there are a lot of other components that are typically part of these units, such as residual connections between the layers, batch or group normalization, and also attention modules. As mentioned before, I aim to build a very simple and easy to understand model, and that's why I only use the main components of this architecture, such as down and upsampling, as well as some residual connections. One constraint of diffusion models is that the input needs to have the same dimension as the output. Because of that, the UNet is a great fit for image data. Our model will take a noisy image with 3 color channels as inputs and predict the noise in the image. Because the variance is set fixed, we will only output one value per pixel. That means the model learns the mean of the Gaussian distribution of the images with 3 color channels as inputs and predict the noise in the image. Because the variance is set fixed, we will only output one value per pixel. That means the model learns the mean of the Gaussian distribution of the images. This is also called denoising score matching. Note that there were also experiments with predicting the image mean instead of the noise mean, and both approaches seem to work. One important thing is that we need to tell the model in which time step we are, because the model always uses the same shared weights for each input, no matter if it's 45 or 8. We will talk about this component in a second. The reverse process can also be formulated mathematically like this. We start in xt with Gaussian noise with a mean of 0 and unit variance. Then in a sequence, the transition from one latent to the next is predicted. This makes the model learn the probability density of an earlier time step given the current time step. As mentioned before, during training we just randomly sample time steps and don't go through the whole sequence. At sampling time, however, we need to iterate from pure noise in xt to x0, which is the final image. The density of an earlier time step given the current time step. As mentioned before, during training we just randomly sample time steps and don't go through the whole sequence. At sampling time, however, we need to iterate from pure noise in xt to x0, which is the final image. The density p is defined by the predicted Gaussian noise distribution in the image. In order to get the actual image of time step xt minus 1, we have to subtract this prediction. We need to iterate from pure noise in xt to x0, which is the final image. The density p is defined by the predicted Gaussian noise distribution in the image. In order to get the actual image of time step xt minus 1, we have to subtract this predicted noise from the image xt during sampling. This is just a rough formula to give you an intuition. The exact one in the paper also considers the noise levels better. Again, if you look for a deeper explanation of this, check out Outlier's math video.
This Ramadan, in Gaza, tables are bare.
Okay, now we have captured the 2 most important parts of diffusion models. Finally, let's talk about how we can consider the time step in our model. The neural network has shared parameters across time, which means it can't distinguish between the different time steps. That, however, means it needs to filter out the noise from images with very different noise intensities. To circumvent this, the authors used positional embeddings, which were presented in the transformer model. They are a clever way to encode discrete positional information like sequence steps. Positional embeddings can be visualized like that and have the task to assign a different vector to each index, for example, like sequence steps. Positional embeddings can be visualized like that and have the task to assign a different vector to each index, For example, if you have the values 1, 5, and 10, the corresponding embeddings could look like this. The embeddings are typically calculated using sine and cosine functions for a specific embedding size defined by d in this case. For more details, I recommend to have a look at the Machine Learning Mastery blog post in the video description. The positional embeddings are then simply added as additional input besides the noisy image and used in several places in the model. Now that we are familiar with all the building blocks, let's see how we can implement this in practice. So this is the backward process and the UNet implementation. Let me quickly show you the code so that you see that it's not too much, because I really try to make this model as simple as possible. That's why it's also called Simple UNet. So let's go over this step by step. The incoming image, so the noise, so this, and the UNet implementation. Let me quickly show you the code so that you see that it's not too much, because I really try to make this model as simple as possible. That's why it's also called Simple UNet. So let's go over this step by step. The incoming image.
Yes, it is, bro. Or I mean to do as.
So the noisy image. has 3 channels for red, green, and blue. And we extend these channels by applying learnable filters in these convolutional layers so that we have more and more channels, so the depth of our tensors increases. And this happens until we have 1024 channels. And then in the up channels, we again reduce the size. And besides that, we also increase and decrease the size of the images, and we will see that in a second. All of that happens in these blocks. And in the forward function, we simply iterate over each of these channels. And this happens until we have 1024 channels. And then in the up channels, we again reduce the size. And besides that, we also increase and decrease the size of the images, and we will see that in a second. All of that happens in these blocks. And in the forward function, we simply iterate over each of these blocks, pass it the current image, and get an updated version of the current image with more channels and a smaller or larger size, and then we pass it again. And in addition to that, we also include the time step in form of a positional vector. And as mentioned before, we use positional embeddings for that. And here is how we can calculate them using sine and cosine functions. And this returns.
All right. Good night, guys.